Okay, Module 5C, we're going to talk about pumps and compressors and mixing chambers. We're going to treat both of those equipment types as steady state. Then we're going to look at charging and discharging process, where you're charging a tank or discharging a tank or a bottle. And those are unsteady state. Actually, it's a flowing process, but also unsteady state as you fill the bottle or discharge the bottle. While earlier we talked about turbines that can capture energy from pressure drops. If you want to raise the pressure of a fluid, then you need to use a compressor or a pump. A turbine, you're capturing the energy and taking work out. In a compressor or a pump, you're trying to raise the pressure, so you're putting work in. Here's a diagram of a pump. For a pump, the energy balance, assuming there's no heat loss, and pumps are fairly small, there could be some heat loss, but here let's neglect it. And so the work in, you follow your arrows when you're doing an energy balance. You draw the arrows, you think you're putting work in, there's a motor hooked up to the pump, so work's going in, and the mass is going in and mass is going out at state 2. In at state 1, out at state 2, so the work is equal to the mass flow times the change in enthalpy. Here we're neglecting velocity, and for liquids which are very dense, the velocity is going to be relatively small, very small really, compared to the mass of the fluid that's flowing through and the energy associated with the pressure. So we have work flow is equal to mass flow times specific volume times P2 minus P1, because you recall for a change in enthalpy, where it's just mechanical energy, the work is P or V delta P, and that's what we're going to use for a pump. Okay, so next, again, we're trying to raise the pressure of liquids with a pump, and you'll find that these are very small amounts of work that we have here. Work, again, mass flow times V delta P. When you're doing this in English units, you have to be very careful with your units. Multiply times 0.185 BTUs per PSI feet cubed. Okay, now let's look at compressors. With a compressor, what you're doing is you're putting a gas in and taking the gas out at a higher pressure, going from low pressure at state 1, low pressure, to high pressure at state 2. You're putting work in, power, so that'd be a motor, something like that hooked up, and you may have cooling or you may have heat loss from your compressor. So you may have some cooling. Oh, I've got my Q upside down, but that's meant to be, this here is meant to be Q, heat loss from the compressor. There are some situations where you want to insulate the compressor and try to avoid heat loss, and there are others where you may want to cool it. Why would you want to cool it? First of all, let's look at the energy balance. Work in plus mass times the energy per mass in is equal to mass times the energy per mass out plus heat loss from your compressor. Usually compressors get hot, so the heat is going out of the compressor. Why would you want to cool a compressor? Because if all you're trying to do is raise the pressure of the fluid for some reason for further processing, then other than to produce energy, power, then what you'll want to do is cool it, because a cool gas has a lower volume than a hot gas. Now when you're pumping a liquid and raising its pressure, the volume is very small and it's not changing. When you're pumping or raising the pressure of a gas, you're having to compress actually and lower the volume of the gas, so you've got a force through a distance there, a pressure through a volume that's changing, and the more the volume changes, the more work you're going to have to do to accomplish that. So often you'll cool the compressor to make the volume smaller by cooling, and that will. Okay, let's take the case where we have an adiabatic compressor and low velocity. Just as in the turbine, the work or the power for the compressor is the mass flow times the change in enthalpy, only this time it's H2 minus H1 rather than H1 minus H2, because now I'm adding work to raise the enthalpy and also to raise the pressure. The work per mass, which we call a small w, is just simply H2 minus H1. Sometimes I'll call that a small w, sometimes I'll put a little bar over it, and that's just convenience for problem solving. Take the work per mass of the compressor. Now, we looked at turbines and we looked at compressors. A compressor raises the pressure of the gas, and a turbine lowers the pressure of the gas. Ideally, the work that we put in the compressor to raise the work that we get out of the turbine as the pressure drops going through the turbine, we should be able to put that work that we get from the turbine into the compressor and take that same gas, raise it to higher pressure, and bump it up and keep going around and around in a perpetual motion machine. Why won't that work? Well, think about it. Now let's look at mixing chambers. A mixing chamber is a fairly simple system where we're adding one fluid, and we're going to treat this as a steady state system. One fluid goes in at state 1. It's mixed together with another fluid at state 2. And then the enthalpy at state 3 will be some average of the enthalpy, or weighted average of the enthalpies of state 1 and state 2. At steady state, the mass flow of 1 times its energy plus the mass flow of 2 times its energy equals mass flow of 3 times its energy plus Q. We'll often make the assumption that Q is equal to 0 or treat an adiabatic mixing chamber, where again the mass flow at 3 times the energy at 3 will be a weighted sum of the mass flow at 1 times its energy plus M2 times theta 2. Okay, frequent assumptions that we have is that they're adiabatic, and also that all the lines hooked up to this at 1, at 2, and then the line leaving at 3 are at the same pressure. So with heat exchangers, we're often neglecting the pressure drop. We'll do the same thing for a mixing chamber, at least for the time being, and let pressure 1 equal pressure 2 equal pressure 3. Also, we're going to neglect kinetic energy changes frequently. And then we can do the energy balance as M1H1 plus M2H2 equals M3H3. We also can do a mass balance, which is probably obvious, but we'll put it up here anyway, that M1 plus M2 is equal to M3 because the two streams coming in will equal the stream coming out. Now that's assuming that we have steady state. Let's get an example. 30 kilograms of dry outside air is mixed with, at 37 degrees C, hot air is mixed with cold air at 7 degrees C to produce 27 degrees C air mixture. So you can imagine that if we add some cold air at 7 degrees C, we won't need as much because it's colder than the final product to produce the final air at 27 degrees C. Here's our diagram of our system. Mass 1 is equal to 30, T1 is 37, mass 2 is unknown, T2 is 7, and again mass 3 is the sum of the mass 1 plus mass 2, and T3 is 27. If I look up my enthalpies from the table, from the air tables, then you can get these enthalpies and solve the problem. You could just well do it, and so here's the solution. Take a minute, convince yourself it's true with those enthalpies, but what I'd like you also to do is use that using Cp times T of the air. Make your reference state for the air 0 degrees C, so that would be Cp times Tn is equal to Hn, or Cp times T1 equals H1, and so on. Try and solve it that way also. You should get pretty close to the same answer. Mass 2 is equal to 15 kilograms per second, and so the total mass will be 45. Okay, we've looked at steady state flow systems, and now let's look at unsteady processes. And this is when you have a tank or something that can accumulate energy or can accumulate mass and energy, then we have to go back and recall our accumulated term, which, if you recall, the energy accumulated is the change of m times u, the mass times the internal energy of the system, stored energy. So let's look at this mass charging this tank. If we take the mass flow and we do a differential balance, mass flow times Hn minus the Q leaving, that would be equal to the stored energy. So I'm calculating the accumulated is with respect to time, dmu dt, because remember, mu is the total energy in the system, mass of the system times u of the system. d dt, the change with time of that energy, would be the rate of accumulation of that energy. Often you'll find it easier, or more straightforward, I should say, to integrate that and do what's called an integral balance, so that we look at state 1 and state 2, and the sum of all the mass, that's what an integral is, a sum. The sum of all the mass flow times enthalpy n minus the sum of all the Q's in is equal to the change over time of the mass times internal energy of the system. If it's adiabatic, then Q goes to 0, and this is the result that we have. If you have a constant mass flow and a constant Hn, then we can say that the mass flow times Hn, take that outside of the integral, times the integral of dt, mass flow Hn outside, constant, integral of dt is the integral of dmu, and the integral of dmu is just m final u final, or m2 u2 minus m1 u1. Integral of mu is just of dmu is just mu evaluated between the limits. So our final result is that mass flow in times Hn times the delta T, which is really just the time it took to fill the tank, is equal to the change in internal energy of the tank. So we need to do an example. 100 kilograms of 30 degrees C air is added to an insulated tank containing 1 kilogram of air at 30 degrees C. Determine the final temperature and pressure. So let's look at this as m dot delta T times H at 30 degrees equals m final U final minus m initial U initial. Now I'm going to use this with equations, ideal gas equations, and we'll take the energy of the air coming in will be our 10 kilograms times, here what I have is CV plus P, CV delta T relative to T reference, plus P times Vn, and that's pressure times the specific volume N, is equal to delta mu. So that would be m final, which is 11 kilograms, because it's obvious if you added 10 kilograms to the tank and you started at 1 kilogram, you'd have 11 kilograms at the end. So 11 kilograms times CVT final minus MIUI, which is 1 kilogram times CVT initial. If we let T reference equal to 0 degrees C, and we let PV equal to R over molecular weight Tn, again that's from the ideal gas equation, this result here. However, we have to be a little bit careful here, whereas up here we're using degrees Celsius, this Tn has to be in degrees Kelvin because we're solving it from the ideal gas equation. Little subtle. To be honest, this problem is probably easier just putting everything in Kelvin and solving it that way. So I would recommend that you try it that way and see if you get the same answer. Plugging all the numbers in, you find the final temperature is 140 degrees C. Now we can use the volume to find the final pressure and just plug back into the ideal gas equation. You know the final temperature now. You know that the initial volume equals the final volume. You can calculate the final moles, which is N2, and reducing it down to P2 without putting any numbers in until we have to. Notice that the ratio of N2 to N1 is 11 to 1. The ratio of the moles is the same as the ratio of the mass, 11 kilograms to 1 kilogram. And our final pressure is 11.4 bar. So fortunately we haven't expanded the tank, but you have to be careful when you start raising the pressure of a tank. Make sure you have a tank that can handle the increased pressure. Okay, let's look at another example, this time using tables, because again, we want to be able to solve all these problems using either equations, ideal gas equations, or using tables if you have tables available. So let's take a look at this one where 10 kilograms of superheated steam at 20 bars and 240 degrees is added to an insulated tank containing 1 kilogram of saturated steam, 1 bar. So this is the idea. M dot delta T is 10 kilograms over time. And now we're using steam, similar to our last problem, only now we're adding steam to a tank containing steam instead of air. Here we look at our properties process table and set that up. And we have three states. We have the input state, we have the initial state, and we have the final state. So put in the data that we know. Coming in, it's at 240 degrees and pressure of 20. We can look up the H as 2876.5. Here we need H for the input stream because H is the stored energy of a moving mass, and it's moving coming into the system, so you have to add the flow work. At state 2, we have the pressure. The initial state, we had the pressure, and we had the quality. It was given to be a saturated vapor at the beginning. So that's two properties about that state. I'm also going to mark down here that we have V0, the specific volume. Here we'll call that V0, and we can find that as one of our properties. We can look up the internal energy, and then notice that V0 at the final state, the specific volume is the initial specific volume divided by 11, because now we have 11 kilograms, whereas at state at the initial state we had only 1 kilogram. So the volume has gotten, you have the same total volume but more mass, so ratio that out and you can find the final volume. And that's kind of what I call the process link in this problem. That's a process link that allows us to find something about the final state from a previous state. Using data from the tables, we find all those properties, and we can calculate the final internal energy from the energy balance. Plug in the properties we know, use the energy balance to find the final internal energy. Use the volume from state 2 to find the volume at state 3. Again, we said that was 1/11th of the volume at state. Let's say the final volume is 1/11th of the initial volume. Now we have two properties for the final state, U and V, and now we can find the pressure at the end and the temperature at the end as a function of these two properties. Now that's not an easy thing to do, but it can be done. Here are our properties, and that's the solution to it. So go home and try that, or I guess you are home. Just try that, plug that into your calculator and see if that see if you can verify all of these properties here that we have for the final state. Okay, we looked at pumps and compressors, where we use power to raise the pressure. We looked at mixing chambers, where we have to do an energy balance and a mass balance, fairly simple mass balance. And we looked at charging, discharging problems. I think of these are unsteady states, so we're combining really a flowing system with a system that's accumulating mass, and that gets to be a little tricky. So these problems require, I would say, careful description of your initial and your final states, and attention to detail in finding when you have to use, for instance, internal energy as opposed to when you use enthalpy. So for homework, go to Chapter 5, and we're finishing Chapter 5. Work as many problems as you can involving compressors, pumps, mixing chambers, and tanks. And just from here, you know how to use the energy balance for closed systems. You know how to use the energy balance for open systems. Now it's just a matter of practice, practice, and more practice. So work away. Last thing, how will the tanks described in this lecture be discharged? It's a good exercise to take the tanks that we have and ask yourself, how would I solve the problem where those tanks are being discharged? So try that as well.